So we are looking at another application of Newton's second law, F is equal to ma. We are applying it on friction on inclined planes. Welcome to my advanced physics class where we discuss modern physics and classical physics. We have a whole new concept for the day, friction. Now imagine you have a block on a smooth surface. So this surface is smooth. There is no friction on it. And this block has a mass m. Now you have the earth beneath it. So if you want to apply Newton's second law on this block, you need to consider the forces in the vertical direction and then in the horizontal direction. That is a Cartesian plane in 2 dimensions, that is 2D. So looking at the forces in the vertical direction, you have the force due to gravity, which is mg. And because the block is not moving vertically anywhere, we have another force which is equal in magnitude but opposite in direction to mg. We call that normal reaction force. So then it turns out that the sum of all forces in the vertical direction should be equal to 0. Then the sum of all the forces in the horizontal direction should also be equal to 0. For the horizontal direction, we don't have any forces in action here. We don't push the object, but in the vertical direction we have n minus mg is equal to the mass times the acceleration in the y direction. But then it turns out this is equal to 0. The whole of this is equal to 0. So if that is equal to 0, then n minus mg should be equal to 0. Therefore, n should be equal to mg. That is really important. That is in the vertical direction. In the horizontal, the sum of all the forces is equal to 0. So that's all the dynamics on this object. Given that this plane is smooth, there are no forces in the horizontal direction, but we have forces in the vertical direction. But let's consider another one. Another one, still, you have the surface to be smooth. You have the block. So of course you have mg, which we've known to be equal to n. And now you exert a force, say to the right. Let me call that force you exert F sub me. So I exert a force. I push this object to the right. And given that this surface is smooth, for the vertical we have n is equal to mg, which we have already calculated. But in the horizontal direction, we have F sub me is equal to the mass of the block times the acceleration in the x direction. Because the surface is smooth, so it will accelerate. And given that this ax is a constant, then ax will be equal to the force you exert divided by the mass of the block. That is case 2. Now, it could also be that the surface is rough. And for a rough surface such as this, let me call this a rough surface. Now, the block still is in equilibrium, is at rest. You have mg on it. You have the normal reaction force. Now, the surface is rough. If you apply a force F sub me, because the surface is rough, the object will not start moving. It will not just start moving. Now, this surface will exert an opposing force on the block. So you feel like you're pushing the thing all right, but it is not moving. It is not moving because there is a frictional force acting in the opposite direction. And friction is an opposing force to a relative motion between two objects in contact. Let's quantify this frictional force. Now, this frictional force, F, is proportional to the normal reaction. And the normal reaction is the force the surface exerts on the block. And that is what quantifies the friction. The more the surfaces are pressed together and the surface exerts more force on the object in contact, then the more friction there will be. So F is proportional to N. And we introduce a constant mu, where mu is called coefficient of friction. The coefficient of friction, mu, lies between 0 and then 1. Now, this constant for every surface, I mean, there is a coefficient of friction for every surface. Every surface has got its own. It could be 0.5, it could be 0.9, it could be 1, it could be 0. When it is, say, 0.5, that means you have to apply a force which is more than half of the normal reaction force in order to cause an object to move on that surface. So half of the normal reaction, if this is 0.5, it will be a tie. A little further than that, then the object will start moving. If it is equal to 1, then you have to apply a force of the normal reaction force to cause the object to move. That is a frictional force. Okay. So there are cases, that is, before moving, before motion, then F sub me minus the frictional force is equal to 0. So F sub me is equal to F, of course, which is equal to the mu times the n, where mu lies between 0 and then 1. Now, just about to move, that is case 2. And F sub me minus the maximum friction. So when the object is just about to move, that means you have applied the force which is giving the object the maximum friction. So you see, friction lies between 0 and 1. So there could be a maximum that the friction can exert or oppose you. If you continue to apply the force, it will reach a point when the friction cannot increase anymore. It has reached its maximum. At that point, it will be a tie. And if you apply a little further than that, the object will start moving. So let's just say it is just about to move. Therefore, frictional force is the maximum. This will also be equal to 0, implying that F sub me be equal to the maximum friction. Now, the maximum friction, F max, is equal to mu s times n. And we call this mu s the coefficient of static friction. The coefficient of static friction. So static friction is an opposing force between two objects in contact where the object has not moved. And at the maximum friction, mu s stands for the maximum percentage that friction can exert as an opposition force on you. And if it is equal to 0.9, it means you have to apply a force greater than 19th of the normal reaction, that is 90% of the normal reaction, before the object will start moving. So if we consider the case where now you apply a force, there is a frictional force on you, but the frictional force has reached the maximum and yet your force is increasing, the object will start moving. So the case where the object is in motion, then F sub me, the force you apply minus F max, will be equal to the mass times the acceleration in the x direction. But we know F max, which is equal to the coefficient of static friction times sort of n. But there is a case where we have to make here. That case is if the object starts moving, you need a less force to overcome the frictional force. So what it means is when the object is yet to move, you have the coefficient of static friction to be high. It could be 0.5, 0.6, 0.7. Let's just say it is 0.5. But as soon as the object starts moving, the frictional force will come down. You need less force to cause the object to move with a constant acceleration. So mu s will change to mu k, coefficient of kinetic friction, which is less than the coefficient of static friction. So F sub me, which is the force you apply, minus the coefficient of kinetic friction, so it is always more difficult to move an object at rest than to keep it at constant motion, times the normal reaction is equal to the mass times the acceleration in the x direction. So F sub me minus the coefficient of kinetic friction is equal to max. Therefore, ax will be the force you apply minus the coefficient of kinetic friction times the normal reaction. The whole of this will be the frictional force divided by the mass of the object. So we establish here that the coefficient of kinetic friction is less than the coefficient of static friction. It is very important to make this point an important case. Coefficient of kinetic friction, that is when the object is moving, will be less than the coefficient of static friction when the object is yet to move. And the explanation has got to do with when the object is on the surface. Now, the irregularities on both surfaces are pressed together. So we call something cold welding. They weld together. You require more force to push it. But then when it has already been set into motion, the cold welding does not happen. The object keeps on sliding over each other, and you require less force to keep it at that constant motion. How do we measure the coefficient of static friction? That is where the inclined planes will come in. So, in order to measure mu s, that is how much frictional force opposes your force. Then, if you put the object on the object as an inclined, now still gravitational pull is like so. But this time around, the normal reaction is not perpendicular, it's not parallel to mg, but it is in an oblique direction to mg. Now, so this angle is theta. So we resolve, if we choose a Cartesian plane, let's call this our y direction, let's call this our x direction, because they are at 90 degrees to each other. Okay. And let's resolve this force into this x direction and then y direction. Now it turns out that if this angle is theta and this angle is also theta, the reason is very simple. Now, the reason is that, now let's imagine that this incline is lying flat on the ground. If it is lying flat on the ground, mg is vertical, normal reaction will be parallel to mg. And that means this component here will also be parallel to mg. They will be lying on the same line. That is when the incline is lying flat on the ground. But as you start moving it up, creating an angle theta, this line, which was initially parallel to mg, will also start moving up at the same angle that this one opens. So when this one opens by pi over 2 radians, this also opens by pi over 2 radians. So when the whole thing is lying flat on the ground, this is mg, this is normal reaction. But if you hold here and start inclining it, if you start inclining this, now what happens is that this direction will also start inclining itself. mg always points vertically down, but the component of mg in the y direction, which is represented by this black arrow, will start opening up. So when the whole thing is now inclined, and then you have this, you still have mg, and then n move that way, and then this line will also incline itself at the same angle theta as this one. Okay. So then if this is theta, then that will mean that this is mg cosine of theta. And resolving one in the x direction, this is mg sine of theta. And let's just say the object will slide downwards. So there is a frictional force F in the upward direction. So when the object is just about to move, now what happens is that then mg sine theta minus F max will be equal to 0. But F max will be equal to mu s times the normal reaction, which will be equal to 0. But the normal reaction, we consider the forces in the vertical direction. N will be equal to mg cos theta. This is very important. So then you see the normal reaction is not always mg. If it is an inclined, it will be mg cosine of theta. So we have mg sine theta minus mu s mg cosine of theta. That will be equal to 0. Now we cancel m, we cancel g, and it turns out that mu s simply be tangent of theta. So the coefficient of static friction of this surface is equal to the tangent of the theta you incline it. So mu s will be maximum when theta is at a critical angle, that if you increase it a little bit more, the object will start sliding. And when the object starts sliding, it will be a whole new dynamics and will not be equal to this. So if the critical angle is 45 degrees, then that will mean that mu s will be 1. So the angle determines, the critical angle determines the coefficient of static friction, critical angle. That is when it starts to move. Now, the same case, but this time round, so this is mg, this is mg sine theta, and this is a normal reaction, and this is mg cosine of theta. And of course, this is theta too. Okay. Now in motion, so this is a frictional force. In motion, mg sine theta as a force in the positive x direction minus F. This time around, F will be mu k times the normal reaction, where the normal reaction is mg cos theta, be equal to m times ax. If there is no frictional force and the object starts sliding down, the acceleration downwards would be g sine theta. But now there's a frictional force, so mg sine theta minus that friction will be equal to max. Now doing your cancellation well, you have ax to be equal to of g sine theta minus mu k g cosine of theta. So that will be equal to sine theta minus mu k cos theta all times g. So then as you can see, if the frictional component is 0, then the acceleration will just be sine theta times g sine theta. Okay. What is it? The y direction is not interesting because there is no motion in the y direction. Now this equation only works if the object is moving down. Now one may try to manipulate this figure so that this quantity beats the sine theta and then make the whole quantity negative. That means ax is in the upward direction. That cannot happen. The fact that you have arrived at this equation means that you applied the whole equation when the object was sliding down and friction was upwards. So you cannot apply the equation when the object is moving up. For that one, friction will be downward, and you have to get a new set of dynamic equation or dynamical equation to solve the problem. Let us consider this inclined with a pulley at one of the vertices. Now, you have a rope which is inextensible passing over the frictionless pulley holding two masses. This is greater than this. Now, there is a tension T in the pulley which has to be the same throughout the string because it is massless. Otherwise, there will be an infinite acceleration. Now, the mere fact that this is greater than that doesn't mean the whole object will have to move downward. It depends on the angle, theta. At a critical angle, a little push or a little increasing angle would cause the whole thing to move downward. So we have mg, this is capital M. This is also capital M, g cos theta. This is capital M, g sine theta. But this is a small mg. Now, when the object starts moving downwards, let's see the dynamical equations that we can write. Then mg, capital Mg sine theta minus the tension T would be equal to max, which is the acceleration in the downward direction. And then we could also write that T, this T minus mg would be equal to small m, but this is capital M. For this mass, this is capital M, but this is small m times ax. The acceleration of this mass is equal to the acceleration of this mass. For the fact that when this string moves by a meter, this also moves upward by a meter. Other than that, the whole string will stretch. So when this mass moves downwards by an inch, this one would have to move upward by an inch, given that this is a frictionless pulley. So this is a dynamical equation we have. And we are solving for T and ax. If we add the two equations, we have mg sine theta. So this equation plus that, T will vanish. So minus mg is equal to capital M ax plus small m ax. And you are getting ax to be equal to capital M sine theta minus small m, both times g. I mean the manipulation of this. And then when you factorize ax out, you have to divide the whole thing by m plus m. So for a downward motion, it turns out that the acceleration in the horizontal direction, that is the x direction, on the inclined will be equal to capital M sine theta minus small m times g divided by m plus n. So when the two masses are equal, when this m is equal to this m, then what do you have? You have 2m at the bottom, and then so for equivalent masses, it is going to be m out sine of theta minus 1 divided by 2m. The m cancels m. Okay, so that will be capital mg sine theta minus mg divided by m plus n. Okay, so that will be ax, and what will be the tension? For the tension, we can, after getting, we can divide the two equations. So dividing the two equations, we have mg sine of theta minus t divided by t minus mg would be equal to capital M over small m. Yes, that's all we can do. So multiplying through by m, capital M small mg sine theta minus small mt is equal to capital mt minus small m capital mg. And then grouping like terms, we have capital M small m g sine theta, and then plus m g is equal to mt plus small mt. So then we have g and g out of sine of theta plus 1 divided by m plus m, that is equal to t. So the tension in the string would be equal to small m capital M times g sine theta plus 1 divided by m plus m. If the two masses are equal, this will be m squared, but this will be 2m, and 1m will cancel that, and you have mg, and then that's what you have. Okay. In the next episode, we are looking at this same case when there is friction on the incline. Stay tuned. Kindly subscribe, click on the notification bell, comment, share, like my videos. Stay tuned.